going to spend a bit of time looking at, well, as the name suggests, integrating functions in time, but looking at these travel graphs, velocity time graphs, things like that. I suppose in a way they're just derivative graphs and how we can get things. Now, if I've got a velocity time graph, to work out the change in displacement, if it's a regular shape, I could start using areas, things like that. Obviously a parabola I can't. But change in displacement would be the complete integral from 0 to 4. Because remember, the area under the curve would go up a level. So the area is going to give me distance, but we want displacement. So change in distance, I would have to work out, area above, area below. Okay? So that's like an integration where the first one is just a straight integral, whereas the second one is an area question. So we're going to work out what's above and what's below to get the answer. So similarly with if I had an acceleration time graph, the change in velocity would be the complete integral, whereas the change in speed, I'd have to be thinking about, area below, area above. If we have to draw, derivative graphs, because at the end of the day, as I say, that's all really these displacement and what have you are. So the function, if you like, is displacement. First derivative is the velocity graph. Second derivative would be the acceleration graph. So if on the original graph, the displacement graph, we have a stationary point, then on the velocity graph, that would become a x-intercept, because we're saying that's when the velocity is equal to 0. If we had an inflection point, so an inflection point, we said one of the conditions was that the second derivative was equal to 0. So if the second derivative is equal to 0, then the one above it must have been a stationary point. Because remember, we had a stationary point, differentiate, we got an x-intercept, so then logically on the acceleration graph, because that is an x-intercept, because it's equal to 0, it must have come from a stationary point on the velocity graph. So if on the displacement graph we have an inflection point, that should translate to a stationary point on the first derivative or the velocity graph. If the displacement graph is increasing, well, increasing means the first derivative is positive, so we know we're above the axis. And if it's decreasing, well, then it must be below the axis. Now, if the original function or the displacement graph is concave up, well, concave up means that the second derivative would be positive. So using the same logic as before, well, if the second derivative is positive, it must have come from something that was increasing. So if the displacement graph is concave up, the velocity graph should be increasing, and the second derivative or the acceleration should be positive, and concave down, therefore, it would go decreasing and negative. So that's how we translate information. Now, I always like to draw the three graphs underneath each other, and then I just vertically translate the information. Well, what type of graph? Well, if the graph is a horizontal line, that's telling me y is equal to a constant value. So if I integrate it, I should get an oblique line, so a line and an angle. But if I was to differentiate it, I should get the x-axis. Differentiate a constant, you get 0. If the original graph was an oblique line, then when I integrate it, I should get a quadratic, so a parabola. If I differentiate it, I'll get a horizontal line. If it's a parabola, then when I integrate it, I should get a cubic. And when it will end up inflecting at the turning point. And that's from what we saw before. An oblique line, when we differentiate it, because differentiate a quadratic, you get a straight line. So remember, integration, area. Integration is indeed area. So we can solve these problems sometimes without drawing the other graph, just using our knowledge of calculus. On a velocity graph, total area gives you distance, whereas the total integral gives you displacement. And on acceleration, total area gives you speed, whereas the total integral will give you velocity. Let's have a look at some HSC ones. So 2003, again we have a trig graph where v is measured in meters per second, t is, is that right? Well, at what times during this period is the particle at rest? Well, this is just solving a trig equation, isn't it? I mean, just saying when is velocity equal to 0? So we want to solve cos t is equal to half, but only for the domain of 0 to 2 pi. That's one of our exact values. We know we're in quadrant 1 to 4. The acute angle would be pi on 3, so we're using radians, not degrees. So alpha 2 pi, not 360, 2 pi minus alpha, pi on 3 and 5 pi on 3. And this is why we must use radians. Because if you had said t equals 60, not true. Right? 60 seconds is not when it happens. It happens at pi on 3 seconds. So whatever 3.1415926535, etc., etc., etc. is divided by 3. That many seconds it happens as. So it must be in radians. So it rests at pi on 3 seconds again after 5 pi on 3. Maximum velocity. Okay, use your knowledge of trig. Sure, you see the word maximum and you think, oh, let's differentiate, find stationary points, etc., etc. But you've got a trig graph. And you know the amplitude of that graph is 4. We know it's been shifted up 2. So we know the biggest that velocity is ever going to be is 6. Okay. So what's the maximum velocity? And if I really want to formalise the solution rather than just write 6, I can say, well, I know minus 4 cos t goes in between minus 4 and 4. And so if I shift it up 2, it goes between minus 2 and 6. So maximum is 6. Sketch the graph. There you go. Making us draw a trig graph again. Okay, amplitude is 4. Shifted up 2. This one's upside down because it was a minus. Period's 2 pi. Mark off the divisions every pi on 2. So there's my axes, but I've shifted up 2. Let's put a dotted line in there that we can use to wind it round. Now, it was it a sine graph or a cosine graph? Cosine. So cosine, we normally start at the amplitude up at the top, but this is negative, so we start down the bottom. So we're at negative 2, then we go to the axis, then we go up, and we go down. So there's my attempt at drawing it for that domain and getting it nice and stationary at the end there. Calculate the total distance travelled. So it's asking for distance, not displacement. So it's an area question. And it's said between 0 and pi. Oh, what a shame. Because if that was on the axis, I could say, oh, well, I know that area would equal that area and things like that, but it's been shifted up. So, all right, I'm going to have to, well, the bit below is 0 to pi on 3, that's going to be negative, and then pi on 3 to pi for the positive bit. Notice I've, on the first one, I've swapped my limits around and made it positive, because at the end of the day, it is the same thing I'm substituting into. So all it means is now I'm going to subtract twice when I sub in pi on 3. So it'll be sub in 0, sub in pi, minus twice sub in pi on 3. And when we calculate that, oh, look at this lovely answer. Oh, beautiful. 4 root 3 plus 2 pi on 3 metres. Yeah, go on, measure that. Yeah. All right. 2004. Looks more like a traditional travel graph, doesn't it? We've got all straight lines, but in fact, look at it closely, it's an acceleration time graph, this one. Acceleration time. So when is the velocity a maximum? And I've got an acceleration time graph. Now, sure, I could work out the equation of each of these lines. I could go and integrate and actually get the function and do all that, but I don't need to, because I know that integration is area. So when is the velocity a maximum? So we know velocity is the integral of acceleration. So we're saying, when is that integral a maximum? Well, it's going to be a maximum. When is it most positive? So when does it have its greatest positive area? It must be at t equals 2, because as soon as we go past 2, we're going to be subtracting areas. Another way of thinking about it, you could say, well, velocity is going to be a maximum when d t is equal to 0. Well, d t is acceleration. And again, acceleration is equal to 0 at 2. So another way you could think about that question. But I don't actually have to do any calculus to get the answer. At what time during the interval is the particle furthest from the origin? So it might be plus, it might be negative. All right. When is displacement a maximum is what this is saying. When is displacement a maximum? Well, displacement is a maximum when velocity is equal to 0. Velocity, remember, is the integral of acceleration. So it's now saying, when would this integral be equal to 0? So when is the area above equal to the area below? They would cancel each other out, giving us an integral of 0. So that's what we're going to try and find. They are nice straight lines, so we can find the areas quite easily. So by symmetry, it's got to be at t equals 4. Because the rectangle plus triangle, well then this triangle gives me the same area as that triangle. So I'm looking for 1 unit along after that triangle. So at 4, those areas would be equal. 2007. It wasn't quite as nice. This time we've got some curvy lines. Okay, coordinates of the points. So they've told us the points just in case you can't read off the graph for some reason. They've told you what those points are, the key points. And this is a velocity time graph. Velocity time graph. Oh, what? You mean we had to remember that? I thought that was 2 units. What? Simpson's rule. Okay. Using Simpson's rule, estimate the distance travelled between t equals 0 and t equals 4. Now you don't know the equation of the curve, but you do know 3 points. So that's what we're going to do. Remember, h on 3, y 0, 4y odd, 2y even, y in. So let's draw up a table of values, but I only know 3 points. I know 0, 0, 2, 1 and 4, 5. So it'll be 1 times the end one, and it'll be 4 times the middle one. Distance between those points is 2, so we get 2 on 3. 0 plus 5, and then 4 lots of 1. So 6 metres is travelled. So we had to use Simpson's rule because we don't know the equation of that curve. So we can only estimate what that area would be. All right. They've told us we're initially at the origin, so during which times is the displacement decreasing? So we know it's decreasing when velocity is less than 0. Now if you look at your graph, I mean it's on the slide before, but you've still got it in front of you. Well, once t is greater than 5, the displacement graph would be decreasing because my velocity graph is negative. Estimates, again we could only estimate because we didn't know the exact area of that first bit, when it will return to the origin. So again, when is displacement equal to 0? Displacement is the integral of velocity, so we're trying to solve when is the integral of velocity equal to 0. Once again, when's the area above equal to the area below? I'll put the graph back in because this is going to be coming handy to solve this one. So when the area above is below, by symmetry, it's a nice straight line. So again, we've got triangles there. So I know those 2 triangles would cancel each other out. So I know that bit's fine. Now, part I, we estimated the area from 0 to 4 to be 6. So we want to cancel that 6 out. So the rectangle after that second triangle, we want to have an area of 6. So in there somewhere. Let's call it area 4. Area 4 has to equal 6. Well, we know the height of that rectangle. So 5 times whatever that length is, let's call it little a, must equal 6. So 1.2. So we now know it's 1.2 further along from 6. So approximately after 7.2 seconds would be the answer. Sketch displacement as a function of time. So I have the velocity graph. I say I like to put the information in straight underneath and translate key information down. So all right, it's originally at the origin, so let's put that in. T equals 0, x equals 0. So I know that point's there. We estimated that when t equals 4, x was equal to 6. So I'll plot that point in. We said by symmetry, it would also be 6 at x equals 6. The two triangles cancelled each other out. The area of that triangle is 2.5. That's why it's 8.5 in here. So I know we've got a further 2.5. So when x equals 5, when t equals 5, x is 8.5. We know it returns to 0 at 7.2, well, that's what we estimated. So I'll plot that in. All right, this is where it gets a little bit trickier. If I look at the velocity graph, it is steeper between 2 and 4 than it is between 0 and 2. So therefore it must travel more distance between A and B than it does between 0 and A. So therefore I'm not at 2, I'm not going to plot halfway at 3, I'm going to plot below 3. So I've pushed it down below the midpoint there because it's going to travel more distance between 2 and 4 than it does between 0 and 2. When t is greater than 6, velocities are constant, so I know the graph's going to be a straight line. So I can draw that piece in. Okay, I know that's going to be a straight line from there. Now between 4 and 6, I've got an oblique line. When I integrate that, I should get a quadratic function. So I'm expecting some sort of parabolic shape there. And then here, well, I don't really know what function that is, but it's going to be some sort of curve. So I'll just estimate roughly where the curve goes. So there's my graph. Figure beauty, isn't it? All right, let's try this one. Another velocity time graph. We've got the xt. Same sorts of questions, I guess. When is the displacement a maximum? So if displacement is a maximum, we know when is the area most positive, or another way of thinking about it is when is the velocity equal to 0? So we know that's going to happen at t equals 2. Yes, it's also 0 over here at 6, but just looking at those areas, that's going to be a negative value. So it's going to be most positive at t equals 2. At what time does it return to the origin? Okay, so when is displacement equal to 0? When is the area above equal to the area below is what we're saying. All right, again, we don't know the function, but we can assume a few things here. That rectangle there, I know has got an area of 2. I have no idea what the area of that little curvy bit is, but I think it's fair to say that that's symmetric. One hopes it is, otherwise how on earth are we going to do this question? So all right, so that's going to be A. So to cancel out, I now need a rectangle of 2. So what's the width? 2 times what would give me 2? Okay, so well, let's work it out. 2w will equal 2. So w is 1. So I'm going to estimate that it returns to the origin after 4 seconds. So yes, so I've made some assumptions there about that's symmetric and things like that. But what else could I do? I mean, if I don't assume that, I haven't got a clue how to do it. Draw a sketch this time of the acceleration graph. There's the velocity graph. So again, I'll put underneath, I've labelled in the key points. So what do we know? When we differentiate horizontal lines, we get x-axis, because we get 0 when you integrate. So all right, when you differentiate. Okay, so I know the graph is just going along the, t-axis in this case, between 0 and 1 and 3 and 5. I'm assuming that's a cubic. Makes life easier. I mean, it's got that sort of cubic-y. Yeah, let's just assume it's a cube. But again, I mean, if you're justifying what you're doing in your solution, I mean, all they're looking for is, do you understand what's happening here? So if you write down things like this, go, well, I'm going to assume that that's a cubic, and if it is a cubic, then I know I should get some sort of parabolic function. Okay, and it's decreasing, so I know it's negative, it's below the axis. Now, this is where I really have to have a big leap of faith. Well, I reckon by symmetry, the one from 5 to 6 is the same as 2 to 3, and therefore it should have the same shape. But this time, there it is. Okay. See, beautiful graph, don't you think? Right. So 3C, I don't remember how involved, whether they get as involved as those last couple we looked at here there, but